Kepler's laws 1. In physics, a satellite, let's see, we have a choice here. A, could be a human-made object. B, could be a nature-made object. C, could be either a human-made object or a nature-made object. D, is a lamp cowboys use to find where to sit on their horses when it's dark. Okay, I think letter C is the best answer here. But D is also a satellite, because if it's dark and you need to figure out where to sit, you need to use your satellite. You didn't think you were going to get through this whole series of videos without a horrible dad joke, did you? Certainly not. Moving on. The figure shows a satellite, little m, in a circular orbit of radius r around the planet of mass big M. Into the figure, draw and label a gravitational force vector on the satellite. All right. Gravity is going to act just like that, straight towards the center of the planet. The satellite is undergoing uniform circular motion. It therefore has no tangential component of acceleration. It has only centripetal acceleration. It's not going faster, 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 faster. That would be tangential acceleration, or slower, slower, slower. It only has centripetal acceleration, which serves to change the direction. For uniform circular motion, this last component of acceleration conforms to the easy equation. You might have run into this before. If you've been watching any of these videos, we've used this often. Centripetal acceleration is v squared over r. Letter D, derive an expression for the speed required for the satellite to maintain a circular orbit around the planet. Let's start off with Newton's second law. The net force on an object is equal to its mass times its acceleration. Let's look at our picture here. Let me roll this back up to allow you to see this picture. The net force on this little m satellite is the force of gravity on it. Now we're going back to the bottom of the page here. Let's write an expression for the force of gravity on this mass. That would be big G times the mass of the planet times the mass of the satellite divided by the distance between them, which is given as r squared. And that should equal the mass of the satellite, which is also little m, times its acceleration. Now this is centripetal acceleration, which we just showed was going to be v squared over r. Now, can we solve this for v? Let's try it. Little v cancels there. One of those r's cancels right there. I think the speed that we need to maintain circular orbit is going to be big G times big M divided by how far we are from the center of the planet, and then square rooted. Notice that this speed does not depend on the mass of the satellite. It depends only on the mass of the planet, how far away the satellite is from the center of the planet, and of course, the universal gravitational constant. Let's continue by writing the integral and dot product form of the work equation. So this is review here. Work, we might remember, is the force at any particular position dotted with a tiny little displacement, and then we add those all up. Into the figure, draw and label a dx vector, or ds, it doesn't matter. I reproduced the picture here so we wouldn't have to flip back to the previous page. Recall that we had gravitational force vector right there, and a dx vector is parallel to the velocity vector. So that little dx vector, of course, it's extremely tiny, but I need to draw it big enough so you can at least see it, is parallel to the velocity. Should I write that up here? Parallel to the velocity vector. And of course, you know the velocity vector is tangent to the path. Letter G. For a satellite in circular orbit, what is the work done on the satellite by the force of gravity? And explain your answer, please. The work done on the satellite by gravity is 0. That's because gravity is everywhere perpendicular to each little dx. That is, it is perpendicular to v at every point. Over time, what will happen to the speed of this satellite? And the answer is it will remain constant by the work energy theorem. If the only force acting on the satellite is gravity, and if gravity doesn't do any work on it, then the work is zero. Therefore, the change in kinetic energy is zero, which means it's going to maintain a constant speed.